Say something. That is the best way to learn. Yes, Pratik.
Sir, I am just reading the email.
You are just reading. This is, see, this way you are not going to learn. Don't do this. Okay, that's fine. But from
Sorry.
next time, make sure. See, I took some effort to convey the concept, and if there is something crucial, I generally convey in email. So next time, please read it. It
Yes,
takes a.
sir.
See, the point is that once you read the email just after the class on the same day, it will be very easy to understand the concept, and it will take few minutes. But if you
Yes,
skip that, then later on, if you go through that email, it may take hours. Okay, so don't do that. Hmm? Good.
sorry.
Okay, see what we were discussing is as follows. We are discussing the Joule's experiment, and Joule's experiment was a cyclic process. So, Pratik, listen carefully. In step one, what Joule did that he let this mass fall through a distance through a height jet downward. If we ignore all the losses, because we had a lot of discussion, I think with Ayush, and I think yeah, it was Ayush, I guess, that if we ignore all the losses, okay, and if we assume that whatever decrease in potential energy, okay, that is gained by the rotational energy of the rotor, and then ultimately it get transferred to the average molecular kinetic energy of the fluid molecules, and that's this way the fluid gets heated. So what Joule did, so if you see from when this mass falls, there is an increase in the temperature of the rotor. So you are going from 1 to 2, that is path A. Okay, and in this path A from 1 to 2, the only interaction with system is work, because this is an insulated system. So you are transferring the work through this shaft. Okay, I am discussing these concepts again and again, work and heat, because that's what we are going to solve in first of thermodynamics. So from 1 to 2, we have only work input. That's what Joule's noted down, and it is simply, if we can minimize the losses, roughly it will be equal to mgj. Pratik, clear? 1 to 2?
Yes, sir.
Okay. So then what Joule did, in the second step, he removed the insulation. Acha, remember, before starting the experiment, the fluid temperature was equal to the ambient temperature that I mentioned in the last class also. So then he did step one, and then he removed this insulation in step two, and then he waited till this fluid temperature becomes equal to its original temperature, which is also the ambient temperature. Because once you remove the insulation, then then the interaction will be heat interaction. Why? Because energy transfer is taking place across the system boundary due to the virtue of temperature difference. Your fluid temperature is higher than the surrounding temperature. Hence, the interaction is heat interaction. Okay. So from 2 to 1, it's heat interaction. So he was knowing the elevated temperature at point 2, and he was knowing through the thermometer, and he was knowing the ambient temperature. So he came from 2 to 1. And how we can calculate, Pratik, this heat interaction from 2 to 1?
Sir, MC del
Yeah, so
dt.
MCP delta T, fine,
Yes.
perfect. Or MC delta T, since it's a liquid. So this way it's a cyclic process, and what Joule noticed, that if he does this experiment, step one for different jet, and then again he goes from 2 to 1, okay, by removing the insulation and noting down the elevated temperature and the ambient temperature he knows already. What he found, that delta W is always proportional to dou W is always proportional to dou Q. This dou is for path function. Okay, so this is not an exact differential. You cannot write dW. It's dou W. Okay.
Sir,
Yes, please.
sir, on the that graph on the
Yeah.
right side, sir,
Yes.
what is there on x-axis and y-axis?
Oh, yeah. You can take any intensive variable, right? Who is it? Bhavna or who else?
Yes, sir, Bhanu.
Bhavna, you can take any PV. It's a state, right? So it doesn't matter. Yeah, for a state, you need two variables. Third one is already decided for this pure substance. So you can take PV. It doesn't matter. Okay.
Yes, sir.
You can take entropy also, entropy, temperature, because for state one, these properties are uniquely defined, right? And for state two also, So it doesn't matter what you take. That's why there is no labeling, whatever you wish. Okay. Achha, why there are two axes only, Bhavna? Because there are so many thermodynamic properties: entropy, enthalpy, pressure, temperature, volume. So why there are only two axes? Any idea? I guess.
Because if we will define two of them, then we can define
Yes,
others
very good.
in
Very good.
terms of them.
True. So that we will see what Bhavna said, that we will see that for a pure substance, if you know the two intensive properties, you can calculate everything. Okay. Then fine. So your doubt is clear, Bhavna?
Yes.
Okay. So go ahead. Let's see. So now this delta W is proportional to dou Q, and we discussed that since when Joule was establishing these concepts, it was assumed that heat is not the form of energy; it's a fluid, invisible fluid, and that's why he was not able to put the equal sign. In order to make them equal, because unit of heat was calorie. Okay, so in order to make this quantity equal, he has to put one equivalent, that is called J, joules equivalent. Later on we know that it's a 1 joule, which is 1 calorie is 4.18 joule. Okay, so if we express after joule, if we express everything in terms of joule, which is now the formal unit of work, energy rather than work, energy, any form of energy, whether energy in transit or energy as the property, energy in transit in work and heat, energy as property is the energy capital A, then there is no need of J, and then we can simply say dou W is dou Q in a cyclic process. Okay, how Joule wrote this statement? Let's see. Since he did the adiabatic process, what he says, there exists for every thermodynamic system a property called energy. The change of energy of a system is proportional to the mechanical work done on the system in an adiabatic process. Okay, why he said that? So wait, so probably you are not able to infer this statement given by Joule. That will be clear in the next slide. So right now what we know, that in a cyclic process from 1 to 2 we know dou W, and from 2 to 1 we know dou Q. Remove this Joule equivalent, we are expressing everything in terms of Joule. Okay, so if we extend it, or in fact if we confine ourselves till the Joule's exponent itself, since there is no work done from 2 to 1 and there is only work done from 1 to 2, so whatever work is done from 1 to 2, that we can say is the work done in this whole cyclic process, because going from 2 to 1 there is no work done, volume is constant. Okay, volume is constant, you are not doing any shaft work, shaft is stationary. Okay, so from 2 to 1 there is no work done, only from 1 to 2 there is work done through path A. So we can put a cyclic integral here. Similarly, there is heat interaction only from 2 to 1, not from 1 to 2. Okay, because from 1 to 2 it was insulated. So cyclic integral of delta W is equal to cyclic integral of dou Q. So you can do some algebra and then you get this, that cyclic integral of difference of dou W minus dou Q is equal to 0. Now let's pause at this point. So Chinmay, you can hear me?
Yes, sir.
Yeah.
Yes, sir.
So whenever you find this cyclic integral of something is 0, what it conveys? Any guess?
So the
Well, you are knowing
the
that-
change in energy is 0?
Rather than energy, say it general, that whenever a cyclic integral of something is 0, what is that something? What we should call that something?
So
Say
the
it
change
more
in
general.
energy is equals to 0.
No, don't say
That
it
is a
energy.
state,
State
function.
State function rather than say it's a thermodynamic property or a state variable. Fine. Property is also fine. Okay. Because property is something which a system contains. Okay. So whenever you find cyclic integral of something is 0, that something is going to be a property. That's for sure. In thermodynamics, it's a thermodynamic property, which we also know as state variables. Both are fine. Okay. Because state is described by thermodynamic property. So both are analogous. So there is nothing confusing. Someone can say state variable, someone can say thermodynamic property. It's same, because state variables is nothing but thermodynamic property. So since we are getting cyclic integral of this bracketed term here, dou W minus dou Q equal to 0, this bracketed term must be a property. And what we call that property, Chinmay?
Sir, the internal energy, the change
No,
in
energy. Again, you are energy, not internal energy. It's energy. It may be internal energy if E doesn't contain other terms. Say it energy. Now there is no scope of confusion. Chinmay, is it clear?
Okay.
Or
Yes, sir.
yeah, it's not internal, it's energy, which contains all form of, internal energy is sub part of this key. Okay. So
Okay.
never make this mistake that it's energy. Okay.
Okay, sir.
Just a small, okay, here there is no read. You can refer to lecture 1. Acha, you guys can find out my lecture slides, right? It's in the class materials. You have located it, I guess? No, no one has located. All the lecture slide I am sharing there.
Yes, sir.
Yeah, okay. If not, then those who don't know, go to class materials, not now, I mean after the class. Every day I upload if something is new. Okay. Okay, so we said since the cyclic interval of dou W minus dou Q is 0, dou W minus dou Q is going to be a property. We'll call this property energy, and energy is a thermodynamic property. And since its cyclic integral is 0, so I wrote d delta is 0, or you can say d is 0 if it's a differential change. So that gives us dou W minus dou Q equal to d going from one state to another state, and that's what we know as. So starting from this cyclic derivation for cyclic process, in general we can infer the first law of thermodynamics, which you know from your J10, okay, that dou W minus dou Q equal to d. Okay. You know it as dq equal to du plus dw, and you frequently use this term d because at that time it was difficult to explain you what is called exact differential or state function, what is called inexact differential or path function. Okay, but now since you are aware, and if you are not, I am repeating. Inexact differential means that differential can change depending on the process. Basically, it's a path function. So if you are going from 1 to 2, you cannot write dw, because going from 1 to 2 every time work can be different. So even if you are making a differential change, that differential work can be different through different processes. So you cannot write dw, you write dou w. It's called inexact differential. Exact differential means it doesn't matter how you go from 1 to 2 or how you make that differential change. It's always going to be same, irrespective of the way you are doing it. And that's why E is an exact difference. So that's why I can write dE. Okay. So that is our first law of thermodynamics. What you studied in J is dq equals to du plus dw. And you, since you were doing it for gases, in fact, mostly ideal gases, you assume that other energies are absent and E is nothing but internal energy. But now we know that E can have other components also. So that is our first law. Okay. Dou W minus dou Q equal to D. So I'll take a 10-second pause. If anyone has anything to say, he can. Otherwise, I think it's quite straightforward. And that's how we formally reach to this, what we call it first law of thermodynamics, the mathematical statement. So I'll wait for a few more seconds. Fine. Remember, this historical point of view is also very important in order to understand a concept. But you never thought that how we reached the first law, but now you know. Okay. Great. Fine. Okay, so this is done. Okay, now again, many people may still argue on thermodynamic work. So I thought I'll give you another, another way to look the thermodynamic work. So you will find that the more general way to define thermodynamic work is a generalized force, which we should call the intensive variable. And displacement is not always a displacement if something is moving. It's a change in extensive variable. I haven't written the change, but extensive variable. Okay. So that is also one classical definition of thermodynamic work. I have written the example. Mechanical work, pressure into volume. Pressure is intensive variable. Okay. Before we move, Lalit, you can hear me or still my voice is breaking?
No, sir, it's fine now.
So tell me what is intensive variable and what is extensive, and then
Sir, intensive variable, it is independent of the quantity.
very good. And of
And
course,
extensive
extensive
will be
then
dependent.
otherwise. So pressure is an
Yes.
intensive variable, and volume is extensive variable because you can add volumes. Okay. So you will see that in all these works, above definition perfects well, works fine. So I'm giving you different, eyes just to, I mean, there is not a very, I mean, all the definitions are correct and all lead to the same mathematical statement or same calculations. Stretching work, if you are stretching a film, surface tension into length or distance. Surface tension is intensive property, length is extensive property. Electrical work, electric field intensity into change in voltage. Okay. So yeah, that's is there okay? So work done. QE is the force, right? Yeah, I think it's fine. Okay. What else? Then magnetic work. It's magnetic field into magnetization. So you can check that there is an intensive variable and there is a change in extensive variable. Okay. Another view to see thermodynamic work which I don't want to discuss because you will get more confused. And so sometime later I will discuss. One very classical definition of thermodynamic work said that if due to a certain energy transfer you can lift a weight, then that energy transfer is work. I will discuss it sometime when you will be, bit free. So right now, let's leave that definition. I'll discuss later on. So that is one way to define thermodynamic work. So Joule's experiment is done, first law done. We know the new another way to define thermodynamic work. Okay. Now here is just a simple example. Okay. So TH should and all others should note it down. You should solve it by your own. If I find that people are unable to solve, then I'll ask TA to solve it. So here my focus is in this question that your energy is actually dominated by the macroscopic kinetic energy, half mv square, not the molecular kinetic energy, and other forms are absent. Read the question. Determine the power required for a 2000 kg car to climb a 100-meter long uphill road with a slope of 30 degrees from horizontal in 10 seconds. Case A at a constant velocity, case B raised to a final velocity. Okay. So here the only component of capital E which is coming in picture is anyone? I already said it, but yes, Lalit, which one?
Sir, can you please repeat the question?
The question is that in this question, so you remember what E contains, capital E, it contains what? Tell me the components of energy, thermodynamic property.
Sir, it contains all types of energy.
No, all types of energy is fine, but what are those?
Kinetic energy.
So say microscopic kinetic energy. Okay. Yeah.
Okay, sir.
Fine. Then
vibrational energy.
No. You are again mixing it everything. Potential energy.
Okay.
Then internal energy. All this vibration and everything rotational comes in internal energy U. Okay. And then you remember I said others, which include chemical and nuclear. So among all these, which one you think will come in picture in this problem? While
sir.
Yes, go ahead.
Sir, potential energy and microscopic kinetic energy.
Microscopic. That's all. So for all of you, just apply simple energy conservation, okay, and try to solve this problem. You have to find out average power, remember, okay, because the time is given. So if you know the work done, okay, then you can simply divide it by time, and then you can calculate the power. How you calculate the work done? Use the first law. Okay, dou W minus dou Q equal to d. There is no dq, there is no heat transfer. So the only mode of here this energy transit is work, and work should be equal to change in energy, and change in energy is nothing but change in K and P. That's all. Why I have given this problem? Because remember this is also first law. It's not like that always the U will change, internal energy will change. Kinetic energy can also change, potential energy can also change. Maybe problem may involve nuclear energy, chemical energy. We have discussed some examples: burning of candle in a closed chamber. Okay, so it's a very straightforward, simply apply. In fact, this is the problem of mechanics. Apply energy conservation. That's all. Ignore all other losses. Okay. So there is no friction also. Huh? There is only this. You have to overcome the potential energy. Huh? Perfect. So Bhavna, it seems easy. What do you think?
Yes, sir.
Yeah,
I'll
just
be.
try. Answer is given. Okay, let's move. Okay, now a few other things which we need to know before we proceed more formally into the various laws. So thermodynamic properties, which we discussed just I think a few minutes ago when we were saying state variables. But let me define it formally because we are going to use it a lot. Either it's a first law or any other law. The formal definition says that these thermodynamic property is nothing but distinguishing characteristics of a system. Basically nothing but the quantities. The quantities to describe or to specify or to give a macroscopic description or a state of the system completely. Okay. These thermodynamic properties can be measured either directly or indirectly. Okay. And change is independent of the path or how you are making that change. Remember, that's why thermodynamic properties are nothing but state variables, and hence can be written as exact differential. I think this, since we already discussed these aspects, definition is quite clear. Okay. So, can anyone tell me any variable thermodynamic property which is not directly measurable? Maybe Charlie, you can tell me any thermodynamic property which you think is indirectly measurable, not directly. Anything comes in your mind? Yes, Charlie, Jan?
Yes, sir.
Just give an example if you can think of.
Any thermodynamic variable.
Yeah, which is not measurable directly. What do you think about temperature?
We can measure it directly.
So tell me the indirect one.
I can't think of any.
Okay, anyone else? Ayush?
Sir, entropy.
Sir, entropy.
That is the simplest example you can think. Entropy you cannot measure directly. You have to measure its change in that heat in transit and the temperature you have to measure. Okay, so we'll see a few more. Enthalpy you can't measure it directly. In some cases, yes, because it becomes equal to heat change. Gibbs free energy you can't measure it directly. There are indirect way to measure it. Okay. So we defined formally thermodynamic properties. We'll revisit this definition and we have at least we will spend 2-3 classes on thermodynamic properties of pure substance, and then we'll solve difficult problems on first law thermodynamics. Okay. Now what else? Now we are going to see what we call as quasi-static process. Many times you say it reversible process. So remember there are two types of reversible process. And reversible doesn't mean that you can revert it back. Never think in that way. Huh? So there is something called internally reversible process. Okay, we call it quasi-static process. What does it mean? It simply means that it happens in a differential way. So every time you disturb the system from equilibrium differentially, means very small, infinitesimally small disturbance, and that's how you move ahead. Okay. Why we are saying that? We are saying that because then in that case you have complete knowledge of intensive variable, how intensive variable varies in that process. For example, pressure. And once you know, then you can calculate the work done, thermodynamic work. Okay. So we can calculate the work done using calculus only for quasi-static process. Then only you have the complete knowledge of that intensive variable, how intensive variable varies throughout this state change. Okay. Internally reversible, what does it mean? It means, and probably this definition will not be very clear right now. We have to wait for a long time, at least 5-6 classes or maybe more than that. But right now, just keeping this thing in mind. Internally reversible means you can only revert back your system to the original state. Okay, so you are going from 1 to 2 differentially with a very small change, and you can come from 2 to 1 differentially with a small change. Only system, not the surrounding. While going from 1 to 2 and coming from 2 to 1, although system has been restored, but probably surrounding has not been restored. This statement will not be clear right now. You have to wait for some classes. What does it mean by system restoration? So internally reversible means this system can be restored without any loss, but surrounding may not be. Don't try to, I can't give example right now. We have to wait. Okay. So that is formal definition of quasi-static process. Now, in order to make it more clear, before this going to this example, the simplest example is right that if you want to expand a gas reversibly, then consider a piston cylinder system, and then of course I think you have seen this example. You have in your earlier maybe in your earlier subject course or maybe in JEE also, that you put some sand, okay, or some mass which is in differential form. It means the pieces of wood, very small fine pieces of wood or sand on the top of the piston, okay, and then you assume that piston is massless, or if you assume piston is not massless, then the initially in the beginning the gas pressure will be equal to the pressure exerted by piston plus the rest of the weight. So you have to take the total weight of piston and the whatever mass you have kept on that piston divided by cross-sectional area of this piston. Now what we will do? You always remove one particle. If you are putting sand, let's say, always remove one particle. Since this particle is very small, there is a differential deviation from the equilibrium, a very small disturbance from the equilibrium. And then again, system will attain to a new equilibrium state. So gas will expand slightly. Again, you remove another particle. Again, there is a small deviation from the equilibrium, and so on. It means this way, this gas will go through numerous equilibrium states or infinite number of equilibrium states. So in a quasi-static process, the system goes through infinite number of equilibrium states in such a way that you can say it's a continuous process. Whereas if you remove this whole sand suddenly, at one time, this whole gas will expand abruptly. So all you know is the initial and final information. There is no information in between. That is non-quasi-static process. We will see in the next slide. And for that you cannot calculate work done, because you don't have the complete information of whether there are, because generally non-quasi-static process there are frictional losses which you can't avoid. Okay. And another thing is that you don't have information of how your intensive variable varied while this expansion, how pressure varied going from 1 to 2 rather than differentially suddenly if you remove the whole sand suddenly. Okay. That is point number 1. So that is the physical picture of quasi-static process. You should make the change or disturbance from the equilibrium differential every time. Another thing which I am going to highlight here, and then we will again revisit when we will go to second law of thermodynamics, that when you do this process quasi-statically, more the extent of internal reversibility of a process, larger the work done can be extracted from the system. Okay, listen to the statement carefully. You can note it down. I haven't written it. I'll explain through this example. What I am saying is as follows. More the extent of internal reversibility in a process, I am taking a pause. More the extent of internal reversibility in a process, or more the extent of quasi-static nature of the process, larger will be the work done extracted by the system. Let's see through this example. Okay. A very interesting experiment. So, on the left, in the leftmost example, see what we are doing here. We have a gas piston cylinder, this piston cylinder system, and the gas is trapped. Okay, and rather than saying me, I'll take help from some student. Let me find some new faces. So Rahul Godler, you can hear me? Golder, sorry. Rahul, you can hear me? Rahul.
Yes,
Yes.
sir.
Yes. Yeah, great. So now can you try to so I am giving you a hint. Okay. What we have done here is that we have kept the total mass constant in all these examples. Okay. Let's say M. So what I have done in assume piston is massless, okay, and assume no friction and ignore the atmospheric pressure for this example. Okay, there is no atmospheric pressure. So tell me in example 1 what I have done. M by 2, M by 2. What does it mean? I mean, you have to guess. Of course, you don't know this experiment, so let's see if you can guess. What is my M by 2, M by 2?
We are keep moving extra masses above the piston.
Very
So
good. So before that, tell me why M by 2, M by 2. What does it mean? So I have divided the mass into two parts. Okay, two blocks. M by
Yes,
2,
yes.
M by 2. Right? Okay, only
yes,
two. Now this is your position 1. Now now remove this M by 2 and keep it at the same height, roughly same height. So what will happen, Rahul, if you remove one M by 2?
then the piston will move slightly above.
So it goes to the second position, right?
Okay. Yeah.
Now what you have? You have only M by 1 block of mass M by 2 at the piston,
Yes.
right? Remove
Yes.
that also.
All right.
What will happen? It will again move with equal distance, right?
Yes. Yes.
This total height is h. So gas is going from 1 to 2. Okay, in 2 steps. M by 2, M by 2 are removing. Okay. So now tell me around, and I can help you also. Tell me that how much work needs to be done if we ignore by the gas, if we ignore all other stuff except this potential energy, gravitational potential energy. So let me help you. Do you think that this, when you remove the first block, ignore the energy which you are going to spend in removing this block? Ignore that energy. So do you think in when we remove this first M by 2 block, there an energy consumption?
If we remove the M by 2
gas
block,
needs to do any work?
I will do the work, but the piston will move.
Ignore that. That just keeping it there. I mean, removing it. That ignore that energy. Then in that case, no, because you are putting it at the same level, right?
Yes.
Yeah. So no work. Fine. Then gas goes up, and then you remove that M by 2 also.
The second M by 2.
Okay. Fine. And then after that, it goes to height h. So tell me, from half of the height to full height, does gas is doing piston is massless?
The internal gas is doing the work because it's expanding, right?
No, there is nothing. Huh? The gas is expanding against nothing. You discuss. You remember? Sorry. So say it's 0. Whether it's abruptly or what, I don't care. Huh?
Okay.
But assume it kind of free expansion. Okay.
Okay. Then work
Not
done is
ideal example of free expansion, but assume it. Okay. So you see that the only work gas is doing is one block of M by 2, which is going by a height of h by 2.
H by 2. Yeah.
The work done by the gas is M by 2 G H by 2.
M by 2 H.
That is MGH by 4.
Okay.
Right. Now you come to some another graph. Let me see. We'll go to the second one. So Sanskar, you can hear me?
Yes, sir.
Let's go to the second example. It's interesting, not boring. Okay, what I have done here, now you can explain it. See, taking the analogy of what we have discussed, tell me the second experiment, what we have done here. Yes. Sanskar. Hello?
Yes, sir.
You can take my help, don't worry.
So,
You at least try. If you are listening, if not, then you can say, sir, I was not listening. I'll go to someone else, no problem. I don't mind, don't worry. If you are listening, then it's fine. Otherwise, let me move.
we are adding masses to the piston now.
No. Okay, you listen carefully. Huh? Acha, Bhavna, you try. Bhavna? Okay, you mute yourself. Bhavna, you try what we are doing in the same second experiment.
So in second one, we have kept the total mass as same like m, but we
Yes,
have divided it into three parts,
three
m by
parts.
3, m by 3,
Very good.
and we
Then,
are removing it by h by 3 height every
yeah, we
time.
see automatically it will go to h by 3, right? Because the movement is corresponding to how much mass you will remove, right? Ultimately, it
Yes.
has to go to height h, right?
And we are as we are removing the topmost mass, we are keeping it on the same height, but we are
Yes,
just removing it from the top of the piston so
very
that
good.
piston
So,
can lift up it up.
perfect. Okay. So, let's say we remove the first block. So, then gas expands. It goes to h by 3 height, right? Yeah. Right, Bhavna?
Yes, sir.
Then again you move another block and it goes to h by 3. And then you again move m by 3, it goes to height h. Now you have to tell me where actually gas is working or how we can calculate. So you just see the left thing, that m by 3, that will you will get your answer. So for first m by 3, is there any work?
So the piston will lift a bit up when we
No,
will
for
remove.
first m by 3. No, for first m by 3, is there any work when you are removing it?
No, sir, since we
No.
are keeping it on the same height.
Very good. So what about the second m by 3? How much work gas has to do in order to lift that second m by 3? How much height
We
it
are
is traveling? H by 3,
h
right?
by 3.
So m by 3, g h by 3, right?
Yes,
And then
sir.
again the last one, how much it is moving?
2h
Tell
by
me.
3.
2h by 3, because it is going from bottom to top. So m by 3, g 2h by 3. You calculate it, it comes out to be mgh by 3. Okay? Thanks. Fine. Similarly, in the last one, we are dividing it in 4 blocks. Yes, anyone is any doubt?
Yes, sir. Can you please explain this once again? I couldn't
Who
understand.
is it?
Sir, Onik.
Sorry, come again. Bit louder. Your name.
Onik.
Anik, see what we are doing. Tell me your doubt, then it will be easy for me, right? Otherwise, I will repeat the same lines. So why don't you tell me?
I didn't understand that while we're removing a block, what is meant by we are keeping it in the same height?
Okay, so you let's say you do this experiment at your home, and let's say the initial whatever the initial height of the piston and masses. Don't consider this height is very large. So at the level of the piston, you put a table. Okay, Anik, fine.
Yes, sir. Yes, sir.
And then remove one block and put on the table. So you are
Okay, sir.
putting the block at the same level, at the same height, right?
Yeah.
So is gas doing any work? If you ignore your work, is gas doing any work?
No, sir.
No, right? Then gas expands, it goes to h by 3 because you are removing m by 3. So correspondingly, it will go to h by 3 height,
Yeah.
right?
Yeah.
So this time, gas has carried 2 blocks, right?
Yeah. Yeah.
So one way is to calculate work done is through this way also. That 2 blocks, how much work is done, then 1 block, how much work is done. That probably will be the direct way. I'm saying why that way? There is a very easy way. That you have to just note down that at what height you have the gas have lifted the various masses. Is the statement clear to you? Anik?
Yes. Sir. Yes,
Yeah,
sir. Yes,
that
sir.
rather than saying that direct work calculation, I'll say do it indirectly. that we need to only care that how much gas has lifted various m/3 blocks. So first m/3 gas doesn't lift it at all because you are lifting, I mean, at the same height. So no work done. Second m/3 is lifted by h/3, right?
Yes, sir.
So gas is doing m/3 g h/3 work done. And the last one has been lifted by 2h/3, right? So
Yeah,
m/3 g h/3. And the very last step there is no block, so gas expands freely. And this way, when you calculate so simply by adding the change in potential energy of the removed blocks, you can calculate the work done by the gas. Simple. Does it make sense?
Yes, sir. I understand now. Thank you, sir.
Well, so similarly, you can divide it in 4 blocks, and then you can calculate the work done the way I did. You can do this as homework, and this comes out to be 3 mgh/8. Now what I did, in order to compare, I made the denominator same, and you can see that in first it's 6 mgh/24, in second it's 8 mgh/24, and in third it's 9 mgh/24. So in the third experiment, the work done by gas is maximum. Now tell me, Anik, which one is more reversible, quasi-static?
So the last one.
Yeah, because you are passing through 3 equilibrium states. In fact, 4. 1, 2, 3,
Yes.
4, right? And whereas in 1 only 2 equilibrium states, in 2 3 equilibrium states, in 4 4 equilibrium states. And that's why I made this
Yes.
statement that more the extent of quasi-static nature of a process, higher will be the work done by the gas or by the system. Okay, remember this statement. It will come again and again, and that's why I took time to discuss this. Okay, we have seen internally reversible. Then there is something called reversible process. Reversible process means it is reversible both internally and externally. Internally, I discussed that system can be restored. It is going from 2 to 1. It will come from 1 to 2. It will come from 2 to 1 differentially. As well as you should be able to restore the system also. Right now, I can't quote the example. The good example will come when we go to second law, when heat interaction will come. Right now, you have to take this definition, like just as, I mean, without understanding much, just consider this formal definition. That reversible means both internally and externally. No doubt, reversible process is also a quasi-static process. But for reverse, when you say reversible only, then it's both internally and externally reversible. Its more physical meaning is when reversed, it's or retraces its forward path and restores the initial state of both system and surrounding. Then reversible process is always frictionless. Then the change, it is always disturbed differentially from the equilibrium, that I already said. Of course, it passes through numerous equilibrium states, if not infinite, numerous. And that's why you can call it a continuous process. And it is always driven by forces whose imbalance is differential in magnitude, same thing. Okay. And you can revert it back at any point by a differential change. Okay. So these are various characteristics of a reversible process. This is just the same quasi-static and non-quasi-static. What I want to say, that when the process is quasi-static or reversible, okay, then you can you should always show it by a solid line, because you know all the equilibrium states, numerous equilibrium states, and it's a kind of continuous graph. You know continuity, so you understand what is continuous. On the other hand, if you are doing it non-quasi-statically, means if gas is going from 1 to 2 abruptly, or you know only few states, then you should show it by dots. Maybe you are knowing few more states between 1 and 2, but you don't know too many, so that you can say continuous. In that case, you should always show it by dots. So whenever you see in any thermodynamic diagram, either PV or VT, whatever state diagram, if there is a dot, remember it's a non-quasi-static process. Many times by mistake, maybe you and me, I can show the non-quasi-static process also by solid line, then you can comment on that at that time. That's why this is non-quasi-static, so you should not show it by a solid line. Solid line means you know all the states, I mean numerous equilibrium states. Right. Okay. So here you see this example. I will not read this. You can read the question. Well, roughly, I'm going to explain you that a gas is trapped initially. You can see the volume of the gas, and the gas pressure is inside pressure is 0.1 megapascal, and outside also 0.1 megapascal. And there is a piston. This piston is just touching a spring. So what do you think, Ayush, that initial any extension in the spring or compression initially?
So there may be extension in this spring depending upon. No,
Oh,
sir,
yeah,
there
okay,
would not
fine.
be any
No,
extension
you don't go into those details. So we can say it's not extended at all, right?
because the pressure is same both the sides.
Yeah,
If the
exactly.
pressure
Because
would
it's
be
already
different, then
equilibrium, so there is no need of extra stretching in the spring. Okay.
yes,
Or,
sir.
okay. Now, let's say that what then we are doing. Now gas is heated. You are supplying heat to the gas. What will happen, Ayush? It will expand, right?
Sir, internal energy will increase, and due to which the pressure will increase.
Yeah,
And it will
whether
expand.
it will increase or not, that we'll see later, but pressure will surely increase because, right,
Yes.
right. Okay. So since pressure is increasing, every time when the pressure will change, automatically it will be adjusted by the spring force, right? So that piston again comes at the equilibrium, right?
Yes, sir.
So we are assuming here that we will do this process very slowly, quasi-statistically, so that it goes through numerous equilibrium states. So you supply some heat, differential heat, it expands a bit, then it adjusts itself, so that since the inside pressure is increasing, there will be heat, again gas expands, and so on. It means at every instant there is an equilibrium, means the net force on the piston is 0. So at any instant, in general, you can write that net force on the piston is 0. So inside pressure of the gas multiplied by area of cross section should be equal to outside pressure, atmospheric pressure, which is constant, into area of cross section and the spring force. Okay. So it means that in this, it is a quasi-static process. You have to assume it, and once you assume it, you can calculate the work done. Very simple. This I am leaving for you. And then what you should achieve, this is from Chemical Engineering Thermodynamics by V.C. Rao. Okay. There are two books by V.C. Rao. One is Engineering Thermodynamics and another is Chemical Engineering Thermodynamics. So basically, there are two ways to calculate work done by gas, and I want you to check it, and then we'll discuss it in the next class. One way is work done by gas is P gas dV, and P gas you can calculate at a general instant, and then you can do it. Another way, and you will see in your answer, and you have to prove it, that one way to calculate is that this is the work done by gas will be also equal to work done against the atmosphere and work done against the spring. And why this is true? You remember when I was defining thermodynamic work, what I said? Work done is always against something. So if I can calculate that how much work has been done against those things, you just add it, you should get the answer. So either you do this P gas dV or the another way, you should get the same answer. So just try to check. Or you can infer from this P dV itself, P gas dV. It should lead to the two terms. One you will see is the work done against atmosphere, and another work done against the spring. That you should see. Then you should be able to see that if there is a spring piston system, okay, then you will find that you can nicely express it. Work done by gas is the change in volume divided by the average pressure, means P initial gas plus P final gas divided by 2. How you do that? You have to write the equilibrium at initial point and equilibrium at final point, so that you can get the Pi gas at the initial and P final gas at the final. You do these calculations, it's very easy. Remember mechanical equilibrium at each point. So the net force on piston is 0 at any instant. So this I want you to work on this problem. And then there is another example. So today's lecture is finished. Very important thing to discuss. Okay. So we have formally entered into the problems on first law of thermodynamics, but only for these gases. Ideal gas. Yes.
Sir,
Yes.
in this question, how the process is happening, that means the path is not given to us. Like we will get the value of x, means the decrease in the length of this spring, and with the help of that we'll calculate the work.
With the help of the Y, you can calculate the pressure also, right? There is equilibrium at
Yes, sir.
every
Pressure
instant.
we can calculate, but how pressure is varying means how pressure is changing with time. That is
No,
not
you know
given to
that
us.
how P varies as a function of X, means as a function of volume, right? That's all you need to know. Can you
Yes, sir.
see?
Means
P is at any general displacement X, starting from the initial position 0. P is equal to PA plus KX by L. You agree?
yes, sir. That is what I'm saying. Means with the help of we can relate it with the help of displacement,
Yes,
but we
that's
cannot
what.
relate with the
Yeah,
temperature and all that stuff.
we don't need that. In fact, from now onwards, as an engineer, you will never try to first focus that whether it's isobaric or isothermal. We don't care. All we care about
Yes,
the
sir.
information.
That is only that the state equation of the gas
Yeah,
means the equation of the
I got your point.
equation of the
But
gas
we
is
don't
not
need
given to
that.
us.
All we need to know how P varies as a function of V. Okay.
Yes, sir. So, sir, we cannot find that equation. Means the equation of the state.
You can. You have to see whether it follows ideal gas law or not. It may not be. Okay. Or any other law that you can always find out. See, you know P as a function of X. It means you know P as a function of volume, right? Right?
Yes, sir. Okay. Okay, we'll
And then you
multiply
have
with
to
A
say whether
and
it's ideal
differentiate.
gas or a Van der Waals gas. I mean, you got
Yes,
the point.
sir.
But we don't care for this problem.
Yes,
Now,
sir.
since you have another class, very important. Oh no, there is no other class. Huh? Good, good. Anything else? Okay, we'll take the advantage. Anything else? Achha, before you discuss anything, let me discuss, and then you can come with your doubts. See, since I take transport phenomena also in this semester, there is a class in my schedule, and that class happens tomorrow. You have class from 11 to 12, and at the same time, with my co-instructor, I try to manage, but it's not possible to take your class. So every Thursday there will be a transport phenomena class of your senior batch. Now I have a kind request to all of you. Can we manage any 1 hour in any weekday apart from designated time for tomorrow? Any free hours, any lab hours probably for which you have registered and no lab is going to happen, physical lab. So I need that 1 hour. And then for tomorrow for 1 hour you are free every Thursday. And can't help. So anyone? I mean, suggest something. See your timetable and tell me. We will going to replace.
Tomorrow you want only 1 hour free, right?
Every Thursday. No. So see, I am not going to take class on Thursday throughout the semester. So there is 1 hour class tomorrow for you, right? So where we can shift that 1 hour. Tomorrow is 1 hour.
So Saturday 3 to 4.
Well, many people will not agree. I mean, I don't know if I agree because Saturday officially I should not take that class. If you don't have any problem,
Thursday, second half is
which one? I'm sorry, which day?
Thursday, second half.
Oh, so tomorrow second half is fine, right?
So we have lab slots, but yeah, this
lab is not going to happen.
Sir,
right?
but but some of the students took the additional in that slots.
That's fine. So additional is 1 hour. Lab hours is 3 hours. So just give me that 1 hour. So whoever are taking additional, please come forward and tell me which one is your busy 1 hour, and then apart from that you can. So lab starts from 2 to 5, that designated hour. So who has additional? Just tell me. I skip that time.
Tomorrow is also free for us.
Which one?
Which day? No one has any lab slot from 2 to 5 also. We can take class between 2 to 3.
2 to 3 is fine, or you want to take some rest? 3 to 4. You tell me. 2 to 3 or 3?
You can take one.
Yes.
3 to 4.
On Tuesday.
3 to 4. Any objection? 3 to 4. So if anyone has objection, he will list. 3 to 4. Any objection? Thursday.
2 to 3 is fine, sir.
Sir, 2 to 3 is fine.
2 to 3 is fine. Okay, 2 to 3. Any objection?
Sir, 3 to 4 is better.
See, please, you have to manage. So, I'll keep it 2 to 3 and then we'll see. Huh? Yes.
So 10 to 11 is also.
Sir, like in Thursday itself,
Yeah.
Thursday, we had a class of PDE. We used to have a class of PDE, but that has been shifted to Saturday. Like it happens from 12 to 1. So
Okay.
if it's possible, you like
See,
to have
I
the
don't have
class
any
from.
problem on Saturday. If you all guys agree, I don't have any problem.
No, sir, I think what he's trying to say is if you can shift to Thursday 12 to 1.
Yes.
Thursday 12 to 1 is perfectly fine if you agree. It's very good.
Yes, sir, that is fine.
Yes, sir. 12 to
That is fine, sir. Thursday 12 to 1.
Yes.
PD teacher instructed to keep that slot free for any possible test or something.
Oh, so so only for test, right? So what I'll do, if there is a class test, then we will see that we'll manage that class on Saturday. Isn't it?
Yes, sir, that would be fine.
Yeah, that would be okay.
Okay, perfect.
Yes, sir.
So I will send an email. Thursday 12 to 1, we'll meet every Thursday. If there is a class test from your PDE, we will shift that class to Saturday. Okay?
Okay, sir,
Fine.
fine.
Perfect.
Yes,
Now,
sir.
if anyone has any doubt, he can come with the doubts. Otherwise, you guys can go for lunch because you have to again. You have class again from 2, na?
Yes, sir.
Yes, sir.
Yeah. Try these problems by your own. In the worst scenario,